Hello everyone, welcome to my channel. In this video, we're going to try to predict gold price using dynamic linear model. Predicting gold price might be very useful if you want to trade gold or you want to predict the volatility of a certain currency pair in forex market. So without further ado, let's get started. So here we are in our R studio. First things first, let's load our package. So the first one here is DLM. DLM is the package to implement dynamic linear model. And then dplyr is for preprocessing our dataset. And then ggplot and plotly are for visualization. Okay, so now let's run these. Okay, so now let's go to the data. I downloaded the gold data price, gold price data, from Nasdaq. So here's the link. I downloaded from there because it's available for free. So you don't need to make an account to get access to that data. I downloaded the data for 1 year. And I have downloaded here, and I'm going to load it as DF now. And here are the first 6 rows of the dataset. So there are 2 things I want you to notice about. The first one is the class of the date. Here we have factor, but actually we want to have it as date. So we're going to need to convert it from factor to character and then to date. And then secondly, this data set is ordered in descending order, meaning that the latest data is at the top row, while the oldest data is at the bottom row. We want to reverse this so that the oldest data is at the top row and get the timestamp 1. Okay, so here are the 2 lines to preprocess our data set. So this line here is to convert the class of date, and the format of the original dataset is month, day, and then year, like this: month, year. Month and then day and then year. So this format is what we pass into the function, and then arrange is for arranging or sorting the dataset based on date year. And here is the new dataset. So it's the pre-processed dataset. And as we can see, the oldest data now is at the top row. The oldest data we have is on June 27th, 2022, while the latest data is now at the bottom row. It's June 23rd, 2023. One more thing I want you to notice though is here's the dimension of the dataset. It's only 250 rows instead of 365, like the full year. This is because we only have the data for business days. So we exclude the weekends and US holidays. So from June 27th, 2022 to June 23rd, 2023, there are only 250 business days. So that's why. Okay, and so this is the date, and this is the close price, and then this is the volume, and these are the open, high, and low prices. And we want to focus ourselves on these 2, the high and the low prices. Okay, so we are going to treat them separately, the high prices alone and the low prices alone. It's not like the high prices is influencing the low price and vice versa. And so to know exactly what we want to predict, we actually need to see this. The latest date we have is June 23rd, 2023. And if we see the name of the day on that date, It's Friday. So our latest data is on Friday, and the next business day would be Monday. So what we actually want to predict is the high and the low prices of gold on Monday, June 26th, 2023. Okay, so now let's plot our series, both the high and the low prices. So here's the code to produce that. I'm going to denote the high prices with blue line and the low prices with orange red line. And geometry then here is for shading the difference between the high and the low prices. Okay, so here's our time plot. You see the y-axis here is USD because the gold price is in US dollars, while the x-axis is definitely the date. Okay, so we're coming back to this in a moment, but for now let's discuss the modeling. So as I said earlier in the video, that we're going to use dynamic linear model, but what is it really? So dynamic linear models, or DLMs, are a specialized case of state space model, which is a very flexible framework for modeling time series data. State space models, well, including DLMs, look at time series data as an output of a dynamic system perturbed by variance. So we have two layers here, or two hierarchies if you will. The first one is the output, and the second is the dynamic system. We call the output layer here as the observational level. So the prices that we see in this time plot are all in the observational level because they are the prices that we observe. And for the system level, it's more subtle, so we can think of the system level price at each time step t as the expected value of the price at each time at time t. DLMs, state space model have this representation of the quadruple of f, g, v, and w. F is the observation matrix, it lies in the observational level, and then G is the system matrix, it lies in the system level, and then V is the observational level variance, while W is the system level variance. Okay, so DLMs are called dynamic because the state vectors is the parameter values, if you will. So if you're familiar with regressions, for example, the classic goal of y equals beta 0 plus beta 1 x. And our goal in regression is usually to approximate the most appropriate value for beta 0 and beta 1. This factor of beta 0 and beta 1 is our state vector in dynamic linear model. So the value of that state vector and the value of our variances in both hierarchies could change over time. That's why it's called dynamic. And we call them as linear because we could add the components which make up into a time series in a linear fashion. Those components might include trend, or seasonal, or autoregressive component, etc. And so in this time plot, we have a trend effect. We can see that from June 2022 to maybe around November 2022, we have a downward trend. But starting from November 2022 onwards, we have an upward trend. And we are going to use the second order polynomial model to capture this defect. And then additionally, we can see a seasonal effect very clearly in this time plot with all these waves. So perhaps we can say that maybe this is the first season, maybe from here to here, or from here to here. Yeah, maybe from here to here. And the second season from here to maybe around here. And then the third season might be starting from here to this point. So the third season might be a longer season than the previous two. The point is that the number of days which make up a season might be different from the first season to the second to the third and so on. So because we might have different days which make up the season, that's why we will implement the form-free seasonal effect DLMs. Form-free meaning that it's free for how many periods, how many days we have. Okay, so we will use two models here, two models. The first one is the second order polynomial model, and the second one is the form-free seasonal effect DLM. Okay, so let's see how we build that, how we code that in R. So as I told you before, we are going to treat the high price and the low price separately, and we will make the models also a little bit different. So the first one is the trend effect for the high price, and we will see later the trend effect for the low price. This will be very similar, just have a minor difference. Now let's go into the high price first. Okay, so this line here is for building the model capturing our trend effect. We use DLM mod poly from polynomial. And there are some arguments which I didn't write here because I just left them to the default values, to their default values, but here are the arguments which I want to explore further. So firstly, since we decided to implement the second order polynomial model, so we set the order equals 2. And then we set also the dv, w, and m0. To explain this better, I'm going to put the state space representation and the mathematical representation, the mathematical equation representation. Okay, so dv is for setting the v, the observational level variance. Since we are dealing with a univariate time series, so it's basically just a scalar. And then the w is for setting the w, the system level matrix. And notice that in R, we only need to specify the diagonal entries because this is actually the covariance matrix of mu, the local level, and beta, the growth level. And since we assume that the mu and the beta are uncorrelated, so the covariance would be 0. The covariance between them, between mu and beta, would be 0. So we only put the variance of the mu first, and then we put the variance of beta next. So for the variance of mu, the default value is 0, but I increase it here. For the default value of beta is 1, and I keep it to the default value. I increase the variance of this, the local level or the mu. Well, it's a personal prior belief, honestly, because we are trying to predict the price on Monday, and the latest data we have is on Friday. And I read this in some articles and journals a long time ago that the stock prices especially, become more unpredictable and have more anomalies on those days, on Fridays and Mondays. So I thought perhaps the gold prices would behave the same way. So that's why I want to leave more room for error. And that's why I increase the variance of mu, of the local level. Okay, and then for the M0 is the initial prior for both the mu and the beta. So it's like, what is the local level at time t0 and what's the growth level at t0? This is what we are addressing in setting M0. The default value is 0 for both entries, for both the mu and the beta. But I think we won't have any gold price to be 0, right? So I just took an eyeball figure from the time plot here and set that to 1920. Maybe it's a little bit too high as well, but it's better than 0. And as you can see later, if you play the code, I will put the code in my GitHub, by the way. But yeah, if you play with the code and try to change the mean here, it won't make much difference actually if you change this from 0 to 1920. It won't make much difference for the forecast, not for the filtered model, not for the model itself. Okay, so that's for the polynomial model. And for the seasonal model, we are using GLM mod Cs because we are using the form-free seasonal effect. And then, yeah, we could have set the V, W, and C, and M. But I just decided to leave them to the default for simplicity. But the only thing that we need to specify is the frequency. The frequency is basically saying how many seasons are there in our time series. And I'm going to set the same for both the high and the low price. Anyway, so let's see our time plot here. Here, I set 4 because I think we roughly have 4 seasons in this time plot. It's like, I don't know, 1, 2, 3, and then 4. Perhaps like that. Or maybe 1 here, and then 2, and then 3, and then 4. It's roughly like that. So I set that to be 4 and leave the rest of the parameters to the default value. Okay, so after we build our trend effect model and the seasonal effect model, we can finally now combine them into one model, one final model. And this is what I mean by linear. We could just add them. In R, we literally type the plus sign. Okay. Oh, by the way, GLM mod poly and GLM mod Cs are going to output some factors and matrices according to the state space representations. And we are going to use them to build the model based on principle of superposition. Okay, so more concretely, we have that F from the trend model and EP from the seasonal model. We are going to concatenate them to make the F of the final model of this model high. And then the same goes from G. With the G, we are going to put the G from the polynomial model in one diagonal and then the G, well, it's called P permutation matrix from the seasonal model and put them in the diagonals of the bigger matrix. And then for the W, it's the same. That's the same for W. G and W works the same way. And then for the V, the variance from the polynomial model is going to be added up with the variance from the seasonal model. So yeah, that's what happens under the hood. And that's the model. And so now let's run these 3 lines here. Again, remember that this is only for the high price, but for the low price, it's going to be exactly the same. The only difference would be this actually. A little spoiler. Okay, so yeah, now after we have that model, the next step is to filter and then forecast. So what is filtering actually? Filtering is the process of updating our inference of the state vectors. And we also have our one-step ahead forecast. But it's not the forecasted value that we're looking for. It's going to just output the mean value and the variance that we need to build the normal distribution for our one-step ahead forecast. So GLM filter is the function to do that. It needs only 2 arguments. The first is the series that we want to analyze, and the second one is the model. We use the model high here. We put in this. Okay, so now let's run this. And I'm going to skip this for now and go to the forecast right away. So the filtered high is now a list of some factors and matrices, and we're going to use some of them. So it's like we will have the mean and the variance of the next value. We will take that from the filtered high and then put it into our forecast function, TLM forecast function, to forecast the price. Okay, and I'm going to store that in forecast high. Forecast high is also a list of some values, some components, and so the forecasted value is stored in F. We see here that the forecasted value, so the quote price, the high quote price on June 26th, 2023 is predicted to be 1942.783. Okay, and the same goes for the low. The only difference here, DLM mod poly, I'm just at the local level, the initial prior for the local level to be different, to be only 1910 instead of 1920. That's the only difference. So let's run this DLM filter because we are now dealing with the low price. So now we have to put the low price, the low column from the data set, and then the model low here. And then after we've filtered it, we have our forecast. We put the we put the output of the DLM filter into as the input of DLM forecast. And then this is our forecasted value. It's also stored in F component. And now we have that our forecasted value, our low price on June 26, 2023 is predicted to be 1902.188. Okay, so before moving on to the visualization, I'm just going to briefly mention this. So these are the equations that DLM filter is calculating. So the updated, we have 4 equations to be updated. And I want you to focus on the ones that we had forecast equation. So it's predicting the distribution. So we are calculating the distribution of yt given the information at time t minus 1. And that's going to be a normal distribution. And then the mean is ft, and then the variance would be qt. And if we want to calculate the mean manually, this is how we would do it. Because the ft would be obtained by matrix multiplication of f, and we got f from the model. It's the f representation from the state space representation, and then we will multiply that with the adaptive matrix A at time t, at the latest time. So we have 250 rows, 250 observations at time t equals 250. So that's why we use this A of 2050. It's like the 2050th A matrix. This is the mean if we want to calculate it manually. But DLM filter, well, from the equations that you have, DLM filter also output this for our convenience, and it's going to be stored in the f component here. And since we only want to take the last value, the 2050th value, so we take the last value here. So I'm going to run these 2 lines to compare. As you can see, they are exactly the same. So I just want to show you that based on the mathematical equation that we learned from our textbook, we can calculate it manually, but DLM package has also provided for us. And then for the variance of the distribution for one-step ahead forecast, they could be calculated by this. So it's a matrix multiplication of F transpose. Well, in that it's F transpose and then times the R and then times F. But for the dimension reasons, I'm going to transpose the F matrix on the second F instead of the first F. And then for the R, what happened here? So yeah, the DLM package is not output the R matrix just like that, but it's outputting the SVD representation. So it's only representing the upper matrix and the D matrix. So if we want to make it into, we want to combine it, arrange it again, assemble it into the R matrix, we need this function. DLM package has provided for us, DLM SVD to var. And yeah, the output of this function, of this line here, is going to be the R matrix. And then after that multiplication, we still need to add the result of those multiplications by V, the variance. So we have the variance is 18. So in other words, our one-step ahead forecast is normally distributed with mean can we, with a mean of 1943.93 and the variance of 18.15294. Okay. But this variance, instead of calculating manually like this, it's provided from the forecasted value. So forecast high, as I said earlier, is storing some values, not only the forecasted value, but also the variance of its prediction. And let's see the variance of it. It's 18.15294. It's exactly the same as this. So let's see if I can go. This is 18, sorry, not 19, 18, and this one is also 18. It's exactly the same. Okay, yeah, so that's it. The same goes for the low price. Maybe I should change the position to here. So we can see the first value here is our manually computed mean of the one step ahead forecast, and this one is what the filter provide us. And this one here is a manually computed variance, and this one is the provided variance. Okay, so now let's visualize our prediction. So I'm using Plotly here. This code block is using Plotly, so I can enlarge the graph. Okay, now let's enlarge this. Okay, so the data here on June 23rd is 1949, and it's projected to be decreasing a little bit on the next day to 1942.783. Okay, the filtered level is denoted by the magenta line, and we are expecting this line to follow the dots quite well. Maybe we can do better here, but otherwise it's doing pretty well. You can see how the lines are following. So as you see the data, the gray dots are the data, by the way. So when the price are going up, the filtered level is also going up. Okay, and this is our prior. No, sorry, not the prior. Well, because our prior is 1920, it's a little bit too high, right? So that's why it's up here. But it's adapting quite quickly. And now let's do the same for the low price. Okay, so here's our graph, and I'm going to enlarge it now. The low price is also predicted to go down, to decrease from 1919 to 1902. Okay, maybe some of you are more concerned with the accuracy of the prediction itself, but let's also look at the direction. Sometimes it's really important to just predict the direction, right? So for the high prices, it's predicted to be decreasing. It's decreasing a little bit from 1949 to 1942. And for the low price, our model also forecasted to be decreasing from 1919 to 1902. Okay, before we see the real data, what really happened in June 26th, 2023. Let's discuss this real quick on how to check statistically our model. So the first one here is to plot our standardized error, standardized one step ahead forecast error. And this is the error for the low price. As you can see, maybe we have a little bit of autoregressive error because it's not really independent. It's not really stationary, sorry. So here we have a non-stationary time series, and that's fine. That's why DLM is quite popular, because it works well with non-stationary time series. With more classical methods of forecasting, we usually require a stationary time series. So sometimes, well, it's more like oftentimes we need to do some pre-processing, like first order differencing or second order differencing, to make it stationary before we implement our methods. But with the DLM, it doesn't have to be like that. So this is for the low price. If you want to see the high price, it looks pretty much the same. Okay, and the second statistical task is to test the normality of the error. So DLMs are a specialized case of state space models because the errors are assumed to be normally distributed. And we need to verify that by using the QQ plot. And as you can see, the tails at both ends is a little bit straying from the straight line. That's for the low. Let's see for the high price now. It's looking a bit better for the high prices. It looks like all the prices are in the right place or in the expected place. Okay, so now let's see how it goes. I've already downloaded the 5-year data, so it includes some data, some prices on July, the beginning of July. And we're going to see here, June 26th, 2023, the high price is 1943, while the low price is 1931. We earlier predicted the high price to be 1942.7, so it's quite close. And the low price to be 1902. 1902, if I remembered correctly. Yes, 1902 there. So yeah, for the low price, we underestimate. That's quite a lot. In fact, we even mispredict. The prediction is incorrect for the direction as well, because for the low price, we predicted the direction to be going down, but it's actually going up. The low price is actually increasing. But for the high price, it is correct. We predict the high price to be decreasing, and that's what really happened. Maybe this QQ plot has warned us. So let's see. Yeah, for the QQ plot of the low price, the filtered from the low price, you see some misplaced dots there. Maybe if I need to make some suggestions, some recommendations, I abruptly set the V and W here. And so perhaps if I set more appropriate values for them, maybe the prediction values would be better. Okay, so that's it for today's video. All the codes that I'm presenting here will be uploaded on my GitHub. I'm going to give the link in the description below. So thanks so much for watching. Please consider subscribing to my channel, TimeSeries. So I'll see you next time. Bye bye.